Good morning, ladies and gentlemen. This is Cristiano Tomassoni from the University of Perugia, Italy. The title of this speech is Additive Manufacturing, Emerging Opportunities for Microwave Components. In this speech, I will present additive manufacturing technology through various examples, and the results I will show during the presentation are the outcome of a collaboration with several individuals. However, during my presentation, I will also provide references to papers where these results are explained in more detail. Let me start with a question. What do all these photos have in common? As you can see, they are related to several different topics, but what they have in common is that they are all connected to the 3D printing. Here you can see that how many applications of additive manufacturing we can have. It has been used in a wide range of fields, including mechanical engineering, the constructions of houses, food industry, also fashion, clothing, accessories, veterinary medicine, and medicine itself for human. Of course, in this presentation, we are interested in the application to microwave components. Well, it is clear that this technology was not properly born for this area, so we have to understand how to exploit this technology for microwave components. During this presentation, we will see the importance of selecting the right additive manufacturing technology according to the application, because there are so many different additive manufacturing technologies that it is important to select the best one in our case. And then I will also show the importance of an additive manufacturing oriented design because despite this technology allows a wide variety of shapes, in any case it doesn't allow all possible shapes. So it is better to have in mind the technology we will be using for the manufacturing during the design. And then we will see also the importance of the post-processing. We will see in particular two different additive manufacturing technologies, the stereolithography that produces plastic objects and the selective laser melting that instead produce directly metal objects. By the way, additional technologies and details are covered in my distinguished microwave lecture. If you are interested in my distinguished lecture, you can ask your local chapter chair to ask for this distinguished lecture. But what is the main difference between additive manufacturing technologies and the classical subtractive technologies, such as the traditional drilling technique? Well, in this case, we have a block of material and we remove the part of the material by using a drill in order to obtain the desired shape. In the additive manufacturing, instead, we have a completely different approach because we add material in order to obtain the desired shape. We manufacture the object layer by layer by adding material, but we can add material by using so many different technologies. We can solidify liquids by using a laser, or we can also melt powder and then solidify in order to obtain the desired shape and so on. So we have a lot of possibilities. There are so many different additive manufacturing technologies that in 2010 the American Society for Testing and Material decided to categorize all technology into 7 categories. In particular, we have vat photopolymerization, material jetting, binder jetting, material extrusion, powder bed fusion, sheet lamination, and directed energy deposition. Well, this presentation is very short, so we cannot cover all of them. So we will see two examples, one in vat photopolymerization and the other in the powder bed fusion category. Let's start with the vat photopolymerization category. Technologies in this category uses resins, photopolymer resin, which are cured and hardened by using an ultraviolet laser. Here we have the real machinery and here we have the scheme. This machinery consists of a vat, according to the name of the category, of course, that contains liquid resin. Here we have the vat and the liquid resin. Then we have the object to be manufactured here, which is attached to the build platform. Here the object and the build platform. And then above the vat, we have an orientable mirror which redirects the laser beam. Then the platform is lowered, immersing the object being manufactured in the resin until leaving a small gap with the vat. At this point, the orientable mirror redirects the laser beam to obtain the new layer of the object. The new layer, of course, has been obtained by hardening the photopolymer resin. After that, usually a blade is used in order to provide a smooth resin. Why we do this? We do this to remove any possible bubble that may have formed when we immersed the object into the resin. Because obviously we must avoid air bubble inside the resin, as they could result in also when the next layer is created. After that, the process is repeated layer by layer until the manufacturing is completed. Here we are adding another layer. And now let's start with the first additive manufacturing technology, the stereolithography. Well, this technology falls in the category of vat photopolymerization, the category we just described. Indeed, we have a vat of liquid photopolymer resin that is hardened by using a laser. This technology is quite versatile. Actually, not only this technology, but in general, all the additive manufacturing technologies are quite versatile because they allow new classes of components with non-conventional geometries, like you can see here. If we want to manufacture these two components by using the traditional milling techniques, you cannot manufacture just in one step. You need more steps. Here instead you can manufacture in one shot. The accuracy also is quite high because its resolution ranges from 25 to 50 micrometers. It is also a low cost, a quite low cost technology because the resin is quite cheap and also the 3D printing machinery is not so expensive. Indeed, you can buy a machine, a 3D printing machine for $2,000, let's say. It is not too much for especially for a laboratory. It is also easy to use. Indeed, this is plug and play, and this is not common in additive manufacturing technologies. It allows fast prototyping, but unfortunately, we produce plastic objects. So, plastic objects have a limited mechanical performance. They are not highly resistant, and they are also susceptible to deformation under high temperature. I would like to show how this technology works by using this filter. This is a filter, this is a cavity filter loaded by mushroom-shaped pores. In addition, we have also a complex wire of network, as you can see here, and this complex wire of network connects all pores. Let's say that this structure is not very easy to be manufactured by using traditional manufacturing techniques. And this network is also important because, for example, if we change the height of this network, we can change, as you can see, the filter band. But if we change this part or this part, we can also change the position of the transmission zero. So, and with the shape of this network, we can reshape the response. So it is very important to be quite accurate in manufacturing this part. For that reason, we select the stereolithography as the technology for the manufacturing. Before starting to show how to manufacture it, I start with some observation. First of all, there is the need of supporting structures in general for additive manufacturing. This is needed because there could be in the manufactured object some parts that are not self-supporting. I will explain later what I mean. And then another important part is the tilt during the manufacturing, because this impacts on the supporting structures and also impacts on the accuracy, on the resolution of this object. And then we will also see the importance of an additive manufacturing oriented design. Okay, this is the filter, the bottom of the filter after the manufacturing. As you can see here, we have a certain tilt angle, and we select this in order to minimize the supporting structure, the supporting structure you can see here. Of course, all those supporting structures after the manufacturing should be removed. But why we need this supporting structure? Let's suppose we have to manufacture this layer. Consider that the manufacturing of this object starts from the top and then proceed through the bottom. And when we start manufacturing this layer, here in this part, we have not the possibility to attach this layer to the previous one because there is no previous layer. For this reason, we need this holding structure to attach this layer. Of course, this is not necessary when we manufacture this layer here, because this layer can be completely attached to the previous one, because the previous one exists. I want to show you that thanks to the tilt, it is not necessary to add further holding structures here, because we can attach all this layer to the previous. So, as you can see, this is why I say that the selection of the tilt, it is very important and impacts on the resolution, first of all, but also on the number of the holding structures. With this technology, by the way, we also need some post-processing, and this post-processing consists in washing the object by using alcohol, because we have to remove the not solidified photopolymer, because when we finished manufacturing it, there is this liquid that adheres to the manufactured object and makes this this object very sticky. So we have to polish to clean it, and then it is better to cure the material by using ultraviolet lights in order to make it harder, and then the supporting structure must be removed. In addition to that, for our filter, we have also specific post-processing. This specific post-processing is because this is for microwave applications. I will explain it better. The material, the plastic material produced by this technology is plastic. And so it could be, in theory, used as the electric material, but unfortunately the loss tangent is quite high. So if you use it as the electric material, you have a lot of losses, and usually this is something undesired when you are working with microwave components. Instead of using as the electric material, we use this just as a support for the metallization in order to shape the metal. And indeed, our filter is considered in metal. So this means that we need to metallize the surface of this plastic. And to do that, we use the electroplating. The electroplating consists in two steps, at least as we implemented. In the step one, we sprayed the surface with silver paint in order to make the surface conductive, because otherwise the electroplating doesn't work. But after the surface is conductive, you can electroplate it. Why we use also the electroplating instead of just using the silver paint? Because the silver paint itself is not very good, because the resistance is quite high. So it is better to use it just to make the surface conductive and then to electroplate, because with electroplating we can obtain much better results in terms of losses. And this is very important because this is a filter, so low losses are very important. Okay, unfortunately, metallization often requires the manufacturing into two pieces, a base and a cover, because you have to metallize the internal part. So you have to divide, of course, in two pieces and then to assemble it. And indeed, we have the cover before and after the electroplating, as well as the base before and after the electroplating. Once you have electroplated, you can just assemble the two parts. Of course, other metallization are also possible. For example, the electroless plating. And in this case, you can also, by using electroless plating, you can also obtain monolithic manufacturing. That would be very interesting because monolithic manufacturing would be has so many advantages. You have not to screw them after the manufacturing. You have to make lighter, and then you don't need to assemble and risking higher losses because the ohmic contact when you join two parts are not so good. So there are a lot of advantages in doing the manufacturing monolithic, and this is in part possible by using the electroless plating, but unfortunately electroless plating needs in any case holes in the structure in order to allow the liquid to penetrate the internal part of the structure. And this is this is a disadvantage. So let's say that there are some advantages, but also disadvantages, because through this aperture you can have also leakage. And this is the manufacturer's filter. As you can see, this is the assembled filter, and it is visible the metallization, and you can see that is only inside because the external part has been not metallized. But in any case, this is the comparison between the manufactured filter response and the equivalent circuit response. What I want to point out is that thanks to the non-conventional geometry, this filter is quite small, and we have also transmission zero that can be easily controlled. And this is obtained thanks to the versatility of this technology. Indeed, this is the complex structure we have to manufacture, and this part, as you can see here, has been manufactured in only one shot. And this is very important because if you are using for the manufacturing of this filter a traditional technology, for example, the drilling technology, well, in this case it is impossible to manufacture this in one shot. You have to add, you have to have the base, and then to the base you have to add all posts, and then you have to attach this complex network. And at the end, it is much more difficult, and there are problems with the accuracy. So in this case, this technology allows to have a lot of advantages. I would also like to show you this T-Magic manufactured by using SLA. Well, this is not from my group, this is from another group, and you can see more details in this paper. But what I want to show here about this structure is that this is obtained by using electroless nickel plating, and indeed they were able to manufacture it monolithically. This is very interesting, but unfortunately, in order to allow the liquid to go inside the structure and in order to allow the metallization, they put a lot of slots in these waveguides, as you can see. And this is a disadvantage. So you have the advantage of a monolithic structure, but at the same time you have the disadvantage of slots. Okay, this is the results, but in our case it is not important. I can also point out that this is a non-conventional geometry for T-Magic, and also in this case they take advantage of the flexibility of the stereolithography technology. And now let me introduce another category of additive manufacturing technologies, the powder bed fusion. In this case, we use a laser or an electron beam to melt and fuse material powder together. It is possible also to use an electron beam, but for our application it is better to use a laser because usually is much more accurate the object when we manufacture it by using a laser. How it works, this category of technologies? In general, we have a powder bed, as you can see here. The powder bed in the real machinery goes here. Now there is no powder actually, but it goes here. And then the manufactured object is buried inside this powder bed. Then we have a platform. You can see here the platform. This one is the platform in the real machinery. And then above this, we have an orientable mirror that redirects the laser beam. Finally, we have also a so-called new powder stock and a powder roller. The new layer of the object is generated by selectively melting the small layer of powder above the object. Of course, the powder is melted by the high-power laser, and then the new powder platform is raised, while built platform is lowered. Then the powder roller pushes the powder to generate a new powder layer. And then come back. And we are ready again to generate a new layer. The process is then repeated layer by layer until the manufacturing is completed. And let's now see a technology that falls in this category, in the category of powder bed fusion we just described. This is the selective laser melting. In this case, we have a metal powder and a laser to melt and fuse a material powder together. This means that we obtain directly metallic object, and this results in high mechanical performances. And we also can manufacture it monolithically, and this is another great advantage because in this case, we don't need to manufacture the object in two halves because we don't need to metallize the internal part. So we can manufacture directly monolithically, and this is an advantage from the point of view of the weight of this object, because if you manufacture in two different parts, then you have to assemble together, and you need flanges, screw, and this increases the weight of this object. And then when you attach two parts to metallic parts, you risk also that ohmic losses increases the losses of the components. So this is really an advantage, the monolithic manufacturing. The accuracy of this technology is quite high, by the way, because the resolution ranges from 25 to 100 micrometers. Unfortunately, the cost is relatively high. And it is not plug and play, so you need an expert operator. Indeed, several parameters must be set on the machinery. For example, you have to select the power of the laser. If you use too high power, you risk to create a large fuse spot, and this results in poor resolution. If the power is not enough, instead, the powder particles stick one each other without fusing. This results in a fragile component and a component with higher losses. So there are a lot of things to be said, and by the way, the metal powder is also dangerous because it is very the metal powder is very fine, and it may explode. And it is also dangerous because it can be inhaled, and it is dangerous for the health. And that's why this operator wear this strange suit in order to avoid to inhale the metal powder. This is a video courtesy of Swiss 212, a company that works in this area with which I'm collaborating. And as you can see here from this video, the laser creates from the powder bed the object. This is accelerated, of course, and then you have to remove the objects from the powder bed to clean it better. But at the end, what you obtain is a component, a complex component that it is monolithically manufactured. So this is a big advantage, of course. This is a spherical cavity filter we manufactured by using this technology. This is a collaboration between my group and the group of Oscar Antonio Peverini from Turin, Italy. Well, this is the initial design in which we have two spherical cavities connected by a rectangular aperture. Well, spherical filters are not a novelty, but here the novelty is that we use an high order mode, and this means that we use that in order to strongly reduce the losses. Okay. We started from this initial design, but then we moved to this other design in order to make an additive manufacturing oriented design. So here we can understand what does it mean additive manufacturing oriented design. Indeed, we chamfered this iris in order to make easy to manufacture this with this technology, and then we also change the shape of the aperture. Indeed, by using this new shape, this is a self-holding shape, so it is not necessary to insert holding structure inside the aperture. Here instead it is necessary to insert them in order to hold this horizontal wall. The fact to have removed the internal holding structure make this manufacturing possible. Otherwise, it is very complicated to remove the internal structure after the filter has been manufactured. Then the next step is to pass toward a mechanical design in which we added the flange in order to connect the filter with the input and output waveguide, and then we also added two pedestals in order to maintain this more stable during the manufacturing. That, by the way, follow this direction. This is the orientation of the manufacturing. This is the final result, and as you can see, we obtain a very good results in terms of Q factor, because the Q factor of this filter was 7,000, and to my knowledge this is the highest Q factor ever obtained by using an additive manufacturing technology. There is no time to explain better how it works, but you can find more details in this paper. This slide shows the comparison between the measured results and the simulated results. As you can see, there is a frequency shift of 45 MHz, but we manufactured two prototypes, and as you can see here, the response of the two prototypes are practically overlapped. This means that this process has a very high repeatability, and this means that this is a systematic error, and systematic errors can be easily removed. So, to conclude, additive manufacturing is very promising for several RF to terahertz applications, including space applications. Indeed, in the last year, we have seen a lot of published papers which try to extend the applicability of this technology to sub-terahertz and 2 terahertz. And by the way, in the last year, there are also additive manufactured components that are already flying on satellites. This technology also allows monolithic manufacturing. We have seen, for example, by using the Selective Laser Melting, we were able to manufacture cavity filters monolithically. And consider that this is not even possible with classical CNC technology, with the computer numerical control technology, such as, for example, the classical drilling process. And this is very important, and this is a very good result, because in this case we are able to reduce the weight of the component, because we don't have any assembly flanges, we don't have assembling screws, and we also reduce the ohmic losses, because when you join two metal parts, there are problems with the ohmic contact generally, and this creates losses. So it is better also from this point of view. And by the way, in the last years, we have also seen an increasing availability of materials in additive manufacturing. For example, there are excellent ceramic materials available, and with this material, we are able to manufacture smaller components, compact components, and components that are less sensible to the variation of temperature, because this is typical of the ceramic. And of course, additive manufacturing is a very flexible technology, and it allows you to obtain not conventional geometries. However, you cannot do what you want. So, when you design your component, you have to use an additive manufacturing oriented design, because this allows you to obtain better results. Finally, we have seen that some additive manufacturing technologies are very complex and are also very difficult to use. For this reason, the collaboration, in my opinion, the collaboration between additive manufacturing experts and microwave experts is highly recommended. This is, for example, what I have done during all these years. Before ending this speech, I would like to leave you a couple of slides that contains the reference to some of my papers which I wrote in the last years in this topic. Okay, this is the first slide, and this is the second slide. If you are interested in this topic, you can also follow my distinguished microwave lecture in which I give more details. Okay, this concludes my talk. I would like to thank you for staying until the end of the presentation. Thank you very much.